Okay, now we're going to study Flemming's right-hand rule. And where we apply this is whenever we bring a conductor into a magnetic field for the express purposes of inducing a current in that conductor, we can use Flemming's right-hand rule to determine the direction of the current. And we're talking about conventional current here. So what Flemming discovered is if you take your right hand and you put your thumb, first finger and second finger mutually perpendicular to one another, you can apply this rule. And what mutually perpendicular means is if my thumb is pointed up, my first finger would be pointed at 90 degrees to that, which is perpendicular to my thumb. And my second finger would be pointed mutually perpendicular to both my thumb and my first finger, or it would be pointed straight at the camera. So you would hold your hand in this fashion here. Now on the board, I have a north pole and a south pole of a magnet, and I have my magnetic field lines flowing from right to left because they go from the north pole to the south pole. And I have a cross section of a conductor coming straight at the camera here. And what I'm going to do is I'm going to bring that conductor up into that magnetic field lines or magnetic flux. That's a grouping of magnetic field lines. And in express purposes to induce a current in that conductor. So we want to determine which way that current is going to flow. So I'm going to hold my hand like we discussed earlier, and I am going to point my thumb in the direction that I'm moving the conductor. In this case, I'm going to be moving it up. And my index finger is going to be pointed in the lines of magnetic field lines, which is right to left. And my second finger is actually exiting the board or pointing towards the camera. So what that indicates is if I draw a cross-sectional area of the conductor again and I put a plus sign in there, what that means is we are going to have conventional current flow flowing out of that conductor. Another way to think of it is if you have the positive terminal of a battery in a circuit, the conventional current is going to be flowing out of the positive terminal. Now let's look at another case. We'll have another cross-sectional area of a conductor. Okay. And this conductor I'm going to bring down into the field, and we're going to see if that creates a different situation for us. So this conductor is going to be moving downward. So my thumb would be pointing in the downward position. My index finger would still be pointing right to left for my magnetic field lines. And as I bring it down into the magnetic flux, I will have my second finger pointed into the board, or it's going away from the camera. So to denote that, I would draw a circle with a negative sign in it. And if you think about a simple DC circuit, the current would be flowing into the negative portion of the battery, which we would denote as a negative sign here because our current is flowing into the board. Now there is an easy way to remember the Flemming's right-hand rule with just using the names of the fingers that we have been describing here. So if I write down thumb, I write down first, and I write down second. If I take the M out of thumb, that stands for the motion. And some people might say movement. Okay, the motion of the conductor, whether it's up or down. Okay. If I take the F in first, that means the field or the field lines, the direction that they're going. Okay, so we were always pointing from right to left in that manner. And on the second, the C stood for the current, the direction of the current. And remember, we are talking about conventional current flow there. Now remember, this rule applies when we want to induce a current into a conductor. It is very different from Flemming's left-hand rule, which is where we have a current in a conductor in a magnetic field in order to move that conductor within that field. And we're going to study that as well. So look for that lesson on Flemming's left-hand rule. But this has been an application of Flemming's right-hand rule, or the generator effect. Okay, I've brought us over to the bench just so we can see the theory that we talked about at the board applied on the bench here. What I have set up is the exact situation that I had on the board. I have my north pole here on the right-hand side, south pole and left-hand side, so I have my field lines going in that direction. I'm going to be moving my conductor up in this fashion, and I want current to be flowing out, or in other words, current to be flowing in this direction, which will come out to my positive lead on my special device here called a galvanometer. And it basically is a current meter that measures very, very low currents. So I'm going to bring this conductor up, and we are expecting to see a positive deflection of the galvanometer. And we did. We saw 10 microamps there as I did that. So now we're going to apply it in the reverse direction like we did on the board, and I'm going to bring this down, and we're expecting to see a negative current induced. So keep an eye on the galvanometer. And there is an application of the theory that we talked about at the whiteboard. So that is Flemming's right-hand rule in practice.